All right, this tutorial is on the big ideas geometry 5.6, proving triangle congruence by ASA and AAS. So the learning objectives are just to be able to use those two congruence theorems. Really, we're going to be looking at two angles and a side, but the order of the two angles and the order of where the side is matters on which one you are using. So the first one is ASA. If two angles in the included side of one triangle are congruent to two angles in the included side of a second triangle, then the two triangles are congruent. So notice how in the diagram you have angle A and angle D at the bottom. You have angle C and angle F, those are congruent. And the side between them, so this is the included side. The side touches both of the angles that are marked congruent. So that is why in ASA, when the S is in the middle, that means it's the included side. So this is ASA in that order. The difference between that and AAS, as you notice in the diagram, the side is not touching both of the angles. It is not the included side. Still given two angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of the second triangle, then those two are congruent. You can't pick BC of this triangle, which is opposite of the 1 mark, and then pick DE, which is opposite of the 2 mark. Those are not corresponding sides because they don't match up with each other. They need to match up and be touching the same angle. So you have angle A, which has 1 mark, D has 1 mark, C has 2, F has 2. Those are your two angles. But then the non-included side, if you're saying that your first triangle is matching with the second mark angle, your second triangle also has to have the same corresponding matching non-included side. So let's see these in action. Can the triangles be proven congruent with the information given in the diagram? If so, what theorem would you use? So part A looks like the side of a glass building formed by some diagonal beams. And you're given these marks that this angle is congruent, this angle, and this side is congruent to that side. So the one thing that we can assume, because two line segments are being intersected, that the vertical angles that are opposite to each other are congruent. And it looks like you have two angles and a side, but let's see if it's included or not included. The side right here is touching only angle 2 and not angle 1. Same thing over here on the right. So this would be the non-included side version, which is angle, angle, side. Part B, this little umbrella where you have intersecting lines, and it looks like 3 different angles are being marked congruent. There's not enough information to prove that the triangles are congruent. We've never talked about angle, angle, angle as a way to prove triangle congruency. There is one later down the road for similarity, but not for congruency, so we're not dealing with AAA right now. And then part C looks like a staircase. You're given those two triangles, and you can assume that since the triangles are matching up on the same side, that side is congruent to itself by the reflexive property. So you have two angles and the included side, which is the side that is touching both angles, so that is ASA. So notice the difference between part A and part C on where your side is and how many angles that it is touching. On to the second example, writing a proof. So we're given that AD is parallel to EC. That's what these red arrows right here indicate. BD is congruent to BC, and we have to prove triangle ABD to EBC in that order. So start with our 2-column proof. Always start with the given reasons first. And then based on the alternate interior angle theorem, you can prove that these two angles right here marked D and C are congruent to each other. This is your transversal. This DC right here is your transversal between the two parallel lines. So by alternate interior angle theorem, that's another set of angles you can prove. So we're going to mark that A. Then you're given BD is congruent to BC. Go ahead and mark that S because it's a pair of sides. And then because of the two lines that are being intersected, the vertical angle congruence theorem, where the two lines cross at B, can be marked congruent, and that is another pair of angles. So it looks like we have two angles and the side that is between both of them. So we can say by ASA congruence theorem that ABD is congruent to EBC. One thing to be careful of is you are allowed to list for the most part, your statements and reasons in any order. So if you decide to list the side first and then your two angles, just pay attention in the diagram to what's being marked, whether it's ASA or AAS. So the order in listing your statements doesn't matter, but the specific reason that you give, that order will matter. All right, now we're going to write a proof on these two triangles that looks like they are right triangles. You're given that HF is parallel to GK and F and K are right angles. Let's prove HFG is congruent to GKH. Start with our given information. Parallel. We're going to again use the alternate interior theorem because we have a transversal of HG connecting those two parallel lines. And we're going to say that GHF is congruent to HGK, which is this side of the transversal. That's again one of the marked angles. You know that these two angles are right angles, which means they're both 90, which means they're congruent. So right angle congruency theorem is your reason to say that they are the same. That's another pair of angles. And then you have that side, HG is congruent to HG based on the reflexive property. So it looks like we have two angles and a non-included side, two angles and a non-included side. So that would be AAS congruency theorem. Again, for your statements, these can be in any order, but just make sure that you're paying attention to which actual congruence theorem you are using to prove your final result.